according to National Electrical Code Section 250.20. B. Using a transformer to change voltage for lighting is permitted under certain conditions. Firstly, the transformer must be an isolating type, providing electrical isolation between the primary, which is the 277-volt circuit, and the secondary, which is the 120-volt circuit. Secondly, the transformer must be approved for outdoor use, designed to withstand the environmental conditions at the installation site. Thirdly, the transformer and all connections must be enclosed in a suitable enclosure, protecting them from moisture and environmental hazards. Fourthly, the transformer enclosure and all metal parts of the lighting system must be properly grounded. The wire size used for the secondary circuit must be adequate for the load and voltage drop. The secondary circuit must be protected by an overcurrent protection device, such as a fuse or circuit breaker, rated for the maximum load. The mounting height of the flood or spotlight should be considered to ensure proper illumination. It is recommended to consult with a qualified electrician to ensure the transformer and installation meet all applicable codes and safety requirements. Grounding is a critical safety measure in electrical systems. It provides a low impedance path for fault current to return to the source, which helps to quickly trip over current protection devices like circuit breakers or fuses. This rapid response minimizes the risk of electrical shock and equipment damage. In the context of using a transformer to step down voltage for lighting, proper grounding is essential for both the transformer enclosure and all metal parts of the lighting system. The grounding conductors should be sized appropriately based on the size of the ungrounded conductors, as specified in NEC Table 250.122. The grounding electrode system, which typically consists of ground rods, ground rings, or connections to metal water pipes, must comply with NEC sections 250.50 through 250.68. The path to ground must be continuous and permanent, ensuring a reliable low impedance connection. Overcurrent protection is another fundamental safety requirement in electrical installations. Overcurrent protection devices, such as fuses and circuit breakers, are designed to interrupt the flow of current when it exceeds the safe ampacity of the circuit conductors. This prevents overheating, insulation damage, and potential fire hazards. When using a transformer to step down voltage, it is crucial to provide overcurrent protection on both the primary and secondary sides of the transformer. The overcurrent protection device on the secondary side, which protects the 120-volt circuit, must be rated for the maximum load that the lighting fixture will draw. The rating should be based on the nameplate data of the lighting fixture and any applicable rating factors. NEC Section 240 provides detailed requirements for overcurrent protection, including the selection and coordination of overcurrent devices. The ampacity of the conductors must be considered when selecting the appropriate overcurrent device rating. The interrupting rating of the overcurrent device must be sufficient to handle the available fault current at the point of installation. An isolation transformer provides electrical isolation between two circuits, which means there is no direct electrical connection between the primary and secondary windings. This isolation is achieved through electromagnetic induction, where energy is transferred from one circuit to another without a conductive path. Isolation transformers are used for several purposes, including safety, noise reduction, and voltage transformation. In the context of using a transformer to step down voltage for lighting, an isolation transformer can help to protect against ground faults and voltage transits. It also provides a level of electrical separation between the 277-volt source and the 120-volt lighting circuit. The isolation transformer should be designed and rated for the specific application, considering the voltage, current, and frequency requirements. It should also comply with applicable safety standards such as UL 15661, which covers dry-type general-purpose and power transformers. The enclosure for the transformer and connections must be suitable for the environment in which it is installed. If the transformer is installed outdoors, the enclosure must be weatherproof and designed to protect against moisture, rain, snow, and other environmental hazards. The enclosure should be made of a durable material such as stainless steel or aluminum and should be properly sealed to prevent water from entering. The enclosure should also provide adequate ventilation to prevent overheating of the transformer. The National Electrical Manufacturers Association, or NEMA, provides standards for enclosure types, which are used to classify the level of protection that an enclosure provides. For example, an NEMA 3R enclosure is suitable for outdoor use and provides protection against rain, sleet, and snow. An NEMA 4 enclosure provides additional protection against splashing water and hose-directed water. The wire size for the secondary circuit must be adequate for the load and voltage drop. The ampacity of the conductors must be sufficient to carry the maximum current that the lighting fixture will draw. The voltage drop in the circuit must be within acceptable limits to ensure that the lighting fixture receives the proper voltage. NEC Section 310.15 provides guidance on determining the ampacity of conductors, taking into account factors such as conductor type, insulation, temperature rating, and ambient temperature. NEC Section 210.19 A1 provides requirements for branch circuit conductor sizing, including the need to account for voltage drop. Voltage drop can be calculated using Ohm's law, which states that voltage drop equals current times resistance. The resistance of the conductors depends on their length, cross-sectional area, and material. Larger conductors have lower resistance and therefore lower voltage drop. It is important to consider the mounting height of the flood or spotlight to ensure proper illumination of the statue. The height of the light fixture will affect the beam angle, the coverage area, and the intensity of the light. A higher mounting height will generally provide a wider coverage area, but the intensity of the light may be reduced. A lower mounting height will provide a more intense light, but the coverage area may be smaller. The optimal mounting height will depend on the size and shape of the statue, the distance from the light pole, and the desired lighting effect. It is also important to consider the angle of the light fixture, which can be adjusted to direct the light where it is needed most. Consulting with a lighting professional can help to determine the best mounting height and angle for the flood or spotlight. Before installing any electrical equipment, it is essential to consult with a qualified electrician to ensure that the installation meets all applicable codes and safety requirements. A qualified electrician has the knowledge and experience to properly design, install, and maintain electrical systems. They can also identify potential hazards and recommend appropriate safety measures. The electrician will be familiar with the local electrical codes, which may vary from the National Electrical Code. They will also be able to perform the necessary calculations to ensure that the electrical system is properly sized and protected. In addition to consulting with an electrician, it is also important to obtain any necessary permits before starting the installation. Electrical permits are required for most electrical work, and they help to ensure that the work is done safely and in accordance with the applicable codes. The permit process typically involves submitting plans and specifications to the local building department and having the work inspected after it is completed. By following these steps, you can help to ensure that the installation is safe, reliable, and compliant with all applicable codes and regulations. When selecting a transformer for this application, several factors must be considered. Firstly, the voltage ratio of the transformer must match the input and output voltage requirements. In this case, the transformer must step down the voltage from 277 volts to 120 volts. Secondly, the kVA rating of the transformer must be sufficient to handle the load of the lighting fixture. The kVA rating is a measure of the transformer's apparent power capacity, and it must be greater than or equal to the total volt-amps drawn by the lighting fixture. The volt-amps can be calculated by multiplying the voltage by the current. Thirdly, the transformer must be designed for the specific application. As mentioned earlier, the transformer must be an isolation type, providing electrical isolation between the primary and secondary windings. It must also be approved for outdoor use and designed to withstand the environmental conditions at the installation site. Fourthly, the transformer must comply with applicable safety standards such as UL 1561. This standard specifies the requirements for dry-type general-purpose and power transformers, including safety, performance, and marking requirements. Fifthly, the transformer should be energy efficient. Energy-efficient transformers can help to reduce energy consumption and lower operating costs. Look for transformers that meet or exceed the minimum efficiency requirements specified in the Department of Energy Regulations. Sixthly, the transformer should be properly sized for the application. Oversizing the transformer can lead to increased costs and reduced efficiency. Undersizing the transformer can lead to overheating and premature failure. Finally, the transformer should be installed in accordance with the manufacturer's instructions and all applicable codes and regulations. This includes proper grounding, overcurrent protection, and ventilation. The location of the transformer is also an important consideration. The transformer should be installed in a location that is accessible for maintenance and inspection. It should also be protected from physical damage and exposure to harsh environmental conditions. If the transformer is installed outdoors, it must be enclosed in a weatherproof enclosure. The enclosure should provide adequate ventilation to prevent overheating of the transformer. The enclosure should also be properly grounded to protect against electrical shock. The wiring connections to the transformer must be made in accordance with the manufacturer's instructions and all applicable codes and regulations. The wiring should be properly sized for the load and voltage drop. The wiring should also be protected from physical damage and exposure to harsh environmental conditions. The overcurrent protection devices for the transformer must be selected in accordance with the manufacturer's instructions and all applicable codes and regulations. The overcurrent protection devices should be sized to protect the transformer from overload and short-circuit conditions. The overcurrent protection devices should also have an interrupting rating that is sufficient to handle the available fault current at the point of installation. The grounding system for the transformer must be installed in accordance with the manufacturer's instructions and all applicable codes and regulations. The grounding system should provide a low impedance path for fault currents to return to the source. The grounding system should also be properly bonded to the transformer enclosure and all metal parts of the lighting system. The lighting fixture should be installed in accordance with the manufacturer's instructions and all applicable codes and regulations. The lighting fixture should be properly mounted and secured to prevent it from falling or becoming dislodged. The lighting fixture should also be properly aimed to provide the desired illumination. The lighting fixture should be protected from physical damage and exposure to harsh environmental conditions. The wiring connections to the lighting fixture must be made in accordance with the manufacturer's instructions and all applicable codes and regulations. The wiring should be properly sized for the load and voltage drop. The wiring should also be protected from physical damage and exposure to harsh environmental conditions. The final step is to inspect the installation to ensure that it is safe, reliable, and compliant with all applicable codes and regulations. The inspection should be performed by a qualified electrician or electrical inspector. The inspection should include a visual examination of the wiring, connections, and equipment. The inspection should also include testing of the grounding system and overcurrent protection devices. If any defects are found, they should be corrected before the installation is put into service. By following these steps, you can help to ensure that the installation of the transformer and lighting fixture is safe, reliable, and compliant with all applicable codes and regulations. Remember, electrical work can be dangerous, so it is always best to consult with a qualified electrician before starting any project. The National Electrical Code, or NEC, is a widely adopted standard for safe electrical installations. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC provides detailed requirements for the design, installation, and inspection of electrical systems. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is not a law, but it is often adopted by state and local governments as part of their built-in codes. Compliance with the NEC is essential for ensuring the safety of electrical installations. The NEC is divided into chapters, articles, and sections. Each chapter covers a specific area of electrical work, such as wiring methods or grounding. Each article covers a more specific topic within the chapter, such as the installation of conductors in raceways or the grounding of electrical equipment. Each section provides detailed requirements for a specific aspect of the topic. The NEC uses a numbering system to identify each section. For example, Section 250.122 specifies the requirements for sizing equipment grounding conductors. The NEC also includes tables and figures that provide additional information and guidance. For example, Table 310.15 B16 provides ampacity ratings for conductors of various sizes and insulation types. The NEC is a complex document and it can be difficult to understand and apply. However, it is essential for anyone who works with electrical systems to be familiar with the NEC. There are many resources available to help you learn about the NEC, including training courses, textbooks, and online resources. It is also important to stay up to date with the latest edition of the NEC, as the requirements are constantly being updated to reflect new technologies and safety concerns.